Welcome to section 4.3, and this particular section deals with what we call the first derivative test. It is a very special application of the first derivative, and basically what it's going to eventually help us to do, along with what is called the second derivative test, which is next week, we should be able to get a very accurate idea of what a graph will look like just by doing a couple of derivatives. And the first derivative test basically deals with maximums, minimums, and whether or not a function is increasing or decreasing. And realize when we did pre-calculus, I certainly spent more than enough time doing the test. I did those using derivatives because I find it easier than other methods. But we begin by asking to use the graphing calculator to find the minimum and the maximum of these particular equations. So I'm going to start with my default window of -10, 10, 1 and -10, 10, 1. That's where I always want to start, and I may have to change it depending. But then I'm going to plug in the equation, so it'll be x to the fourth minus 3x cubed minus 21x squared plus 74x plus 15. And I'm going to go ahead and graph it and see what I get. Now I see that something's happening way down here, but I'm certainly missing out on where it goes. And actually what I get is after a little bit of finagling with it, I realize that my x or my y minimum has to go way down to about -250. So I'm going to put in -250, and I'm going to change my scale, of course, so that maybe every mark will represent 50, and then graph that. And then I certainly see a minimum right there. So what I'm going to do is, just like we always have, I'm going to do second calculate, and then I'm going to find the minimum, which is option number 3. I need to make sure to get to the left side. Okay, there I'm to the left, quite a bit to the left, but that's okay. And then go to the right, and then here the guess really isn't all that important. Just going to do a guess, and I see that the answer is -3.09, -234.49. And so that's what one of my minimums will be. But then I need to take a look at the general graph again, because I should remember that an x to the fourth power might represent more than just one minimum. There might be another curve in here somewhere, because x to the fourth powers often look like w's. We need to remember that. So what I need to do is I need to go back and see, okay, what happens if I put back to the general one. And we don't seem to get a whole lot here, so let's see if I can change the window a little bit more to see what happens eventually. I'm a little bit concerned that my original problem is not in there right, so let me check it really quick. Okay, so it is in right. So I'm going to change. I see something going on potentially here. If you look right around the axis or fairly close to the axis. So what I'm going to do is I'm going to change my y max just a little bit bigger as well. Let me go to y max being, I don't know, 100. Let's try that. And then once we graph it, let's see what we get there. Okay, we already know down here it's doing something, but look at what happens here. It goes up and there's a maximum here and there's a minimum here. So now what we need to do is we need to find both of those. And so once again, I'm going to do second calculate, and then I'll do the maximum first. The maximum, I need to go to the left of it. There I'm to the left of it. Now I need to go slightly to the right of it. Okay, and then guess, it doesn't really matter where I guess, and it will give me 1.6073.91. And then I need to find this minimum here because it's not an absolute, it's just a local one. We've got a local maximum here, we have a local minimum here, and we have an absolute minimum way down here, the first one that we calculated, which was the negative 3.09, negative 234.49, because from now on it's going to go up forever. And so finally we're going to do second calculate and find the minimum, the local minimum there. Go to the left of it, say about right there, go slightly to the right of it, and then guess, doesn't really matter. And we see that that answer is 3.74 and 36.73. And so what it all ends up equaling when it's all said and done is the following. For number one, we have an absolute minimum at negative 3.09, negative 234.49. We have a relative maximum, and we know it's not absolute because there are parts of this graph that's higher. Relative maximum at 1.60, 73.91. And we have a relative minimum. It's relative because it does do a dip there, but it's not the absolute lowest that it ever gets. And that's 3.74, 36.73. And so we have all of these, the two minimums and the two maximum, or the one maximum, and it just happens that one's absolute and two of them are relative. Question number two would be accomplished in exactly the same way. A couple things that we'd want to look at is, first of all, we have a fifth power, so we know that there's no absolutes here. A fifth power, any odd power, never has any absolute minimums or absolute maximums. So they're going to be all relative, and there's potentially four of them. Just like in number one, since it's to a fourth power, there were three. That's the maximum number that is possible. In to the fifth power, that means the most that it could be would be 4. And we happen to have two relative minimums and two relative maximums. And I'm not going to go through the entire calculator process, but you will want to know how to do this for each one of these. Here are the answers, just so that when you have the time, you need to check these with the graphing calculator. We have a relative minimum at 0.42, 25.51, another relative minimum at 79.19, and negative 7, wow, I forgot how big this number was. It is just gargantuan. Negative 7,637,525. It's way out there, and that may take a long time to guess that much. You know, after a while you just get so frustrated, you say, I'm going to let it be 10 trillion, billion, quadrillion, whatever. But as it turns out, this is the relative minimum. And then the two relative maximums are much more reasonable, negative 1.86 and 49.07, and 2.25, 38.09. And so realize this just is a matter of requiring the graphing calculator and doing what is required. Now, how this ties into this particular section is the fact that we're going to be using what is called the first derivative test. And that begins, or the easiest example is find the largest open interval where the function is changing as requested. In other words, the first derivative test tells us where is it increasing and or where is it decreasing. And we will want to use a number line to do the testing. This is going to be an inequality type of problem. So we are given this function for number 3. F of x equals x squared minus 2x plus 1. And we want to know where is it increasing. Well, to use the first derivative test, what we're going to do is the first thing we're going to do is find that first derivative. So f prime of x is equal to 2x minus 2. This should not be a big surprise. But where we use the first derivative test is the increasing part. What we're asking, since it's increasing, we're asking where is that first derivative greater than 0. Increasing means it's greater than 0. Decreasing would mean it's less than 0. So now all we have to do is to solve this inequality here. I'm going to add 2 to both sides, so 2x is greater than 2, and divide both sides by 2 so that x is greater than 1. And we need to come up, what is the open interval where it's increasing? What's the biggest interval that it's increasing? And that means x is greater than 1, or how we show that is 1 to infinity. And so this is the answer for number 3. Number 4 is going to be similar, but it is a little bit different in that it has the absolute value. And we have to spend a little bit of time dealing with what is the derivative of an absolute value. What we need to do here is to first change this into a complex function, because it's going to equal x minus 8 as long as x is greater than or equal to 8. Because we know if, let's just say, if the number is 8, then the value of this is 0. If this is 25, then this equals 17, which of course is what this equals. But the question becomes, what happens when x is less than 8? Well, it's the exact opposite of this. And let's just look at some examples. So we're saying 8 minus x. Let's say this is 0. If this is 0, the answer is still positive 8. But is that what we get here? Well, if x is 0, 8 minus 0 is 8. So this is the way to create from an absolute value. We have to separate it into 2 different functions. Now, this one's the easiest one to determine. It's always, you know, where is this greater than 0, greater than or equal to 0, or x is greater than or equal to 8, and it's just the absolute value without the absolute values. Everything else, everything less than that, or exactly opposite of this, will be the opposite of this. And so that's an easy way to change this into a usable form that we can actually find the derivative. Now we're asking, where is it decreasing? Well, the first thing we have to do is to figure out what is the derivative in each one of these cases. So, as long as x is greater than or equal to 8, the derivative would be 1, because that's pretty simple, 1. Now the question is it decreasing when f prime of x equals 1? Well, in order to be decreasing, this has to be less than 0, which it is not. And so nowhere greater than or equal to 8 is it going to be decreasing. It's always going to be increasing during nap time. And that should not be a big surprise, because if you think about what the graph of an absolute value looks like, it looks like that. But here at 8, everything above 8, it's increasing. So hopefully everything below 8 is going to be decreasing. Well, let's look. When x is less than 8, f prime of x is equal to -1, which does happen to be less than 0. So that's the time that it's going to be decreasing. So to show x is less than 8, we're going to go from -infinity all the way up to 8, but not including 8. Question number 5. We need to identify the function's local and absolute extreme values, if there are any, and say where they occur. So we can just do some calculations here, look at what the graph looks like, and then go from there. So number 5, we have f of x equals x cubed minus 9x squared plus 27x plus 3. Okay, to find local extreme values, we need to know where's it increasing, where's it decreasing, and all that stuff. So that's where we're going with this. Okay, so the first thing we have to do in order to determine increasing and decreasing is to take the derivative. So the derivative of this is 3x squared minus 18x plus 27. Now, where extreme values occur, if you think about just a generic graph, and we've just taken the derivative means the slope. So what we're looking at is, where is it there? What happens there? What happens there? What happens here? Each and every case, the derivative is 0 because the slope is 0. So, so this is why it makes sense that when we try to find extreme values, either locals or minimums, or absolutes, then all we have to do is take the derivative and set that equal to 0. So 0 equals 3x squared minus 18x plus 27. And I can divide everything through by 3. So we get 0 equals x squared minus 6x plus 9. And then this, luckily, is a perfect square. X minus 3, the quantity squared. I can take the square root of both sides, so I get x minus 3 equals 0, or x equals 3. Now, what happens here is we know something happens at 3. Let's suppose that value is 3 right there. But we don't know exactly, is it increasing on this side and decreasing on this side? Is it increasing and increasing, or whatever? That's what we need to ask ourselves. So what we're going to do is we're going to put this on a number line and say something happens at 3. So I'm going to have to do a test point here and a test point here. So the easy test point here, hopefully you see, is 0. And here I'm just going to choose 4 because it's the smallest number that really makes sense here. So if I plug in 0 into the derivative, because we're asking when is the derivative positive or negative, so I'm going to put in f prime of 0. F prime of 0 would equal 27, and that shouldn't be too difficult to see. So we know that it is increasing at this point. We know it's increasing because this is positive. If the derivative of the point is positive, then that means it's increasing. Likewise, I'm going to have to take f prime of 4. Now this one's not quite as easy to calculate, so it's going to be 3 times 4 squared minus 18 times 4 plus 27. Now after this is all said and done, f prime of 4 equals 3. Believe it or not, that whole thing just boils down to a simple old 3. But this is also positive, which means this is increasing. And so the question now becomes, is this thing that occurs at 3, is this a minimum, a maximum, or really neither? And what we have to ask is, on the left side of 3, it's increasing. On the right side of 3, it's increasing. So it's certainly not a maximum. It's certainly not a minimum, because in order to get either one of those, you need to have increasing on one side, decreasing on the other. So basically, this is what we'll be dealing with next week. Something happens at 3, but not a minimum or a maximum. And so, for right now, all we can say is there are no local extrema. There's nothing that is happening. Well, I mean, there is something that's happening there, but nothing, no maximum or minimum. Ooh, sample number 6. Sample number 6. we have f of x equals the square root of x squared plus 18x plus 162. Okay, we need to, first thing, rewrite this into a user-friendly form. So that'd be x squared plus 18x plus 162 raised to the 1/2 power. Okay, first thing, find the derivative. So the derivative is going to require the chain rule. We're going to take the 1/2 times whatever was in the inside, subtract 1 from that exponent, negative 1/2, but then we have to multiply by the derivative of the inside, which is 2x plus 18. Now this is what f prime equals. I'm going to straighten it up or clean it up a little bit. I understand, or if I take 1/2 times this is going to leave x plus 9 here, because 1/2 times this is x plus 9. And this is all going to go in the denominator with the square root. And so this is the more acceptable way to show the derivative, although some would argue the square root in the denominator is not. That's perfectly fine in this case. This is a user-friendly form, but this is what we're going to put down as our derivative. Now what we need to do is we need to determine, where do things happen? Well, things happen when x plus 9 equals 0, or in other words, x equals negative 9. Something happens when x equals negative 9. And also, something happens whenever this is equal to 0 also, because it's going to make this whole statement undefined. So what we also have to do is figure out, okay, x squared plus 18x plus 162, something happens when it equals 0 as well. Well, the really nice thing about this is this doesn't factor, and in fact if we try to plug it into the quadratic formula, it's not even solvable. So there's no solution here. So that will never equal 0. That's the good thing. So now we have to realize something happens at negative 9. So I'm going to put negative 9 here and choose some values over here. Realize if this did come up with a value, say a value of 5, what I'd have to do is I have to put in a value of 5, and I could choose 0 and 6 and negative 10 over here. But just realize I know something happens at negative 9, and that's the only place something special happens. And so I'm going to plug in my values. I'm going to choose 0 up on this end and negative 10 down at this end. And let me see what happens in f prime. Okay, f prime of negative 10. I'm going to do the more difficult one first. Negative 10 plus 9 is negative 1. And let's see, what do I get down here? Negative 10 squared is 100. Would be minus 180 when we take 18 times negative 10, plus 162, which is equal to negative 1 over the square root of, what, 82? And once I realize, hey, this is going to be some negative number, that's all I need to know. So I know this is a negative number. Okay? Now I'm going to come over here and plug in 0. F prime of 0. F prime of 0 would equal 9 over, okay, 0 plus 162. Well, once again, I look at this. This is going to be a positive number. So in other words, this is decreasing on this interval. It is increasing on this interval. And as a result, that means the thing that occurs at negative 9, if it's decreasing up until then and increasing all of a sudden, that means there's a minimum that occurs. Okay, so we're going to have a minimum at negative 9, and I need the value also. Well, to get that value, all I have to do is plug that into f. So I'm going to plug in f of negative 9, which equals the square root of, okay, negative 9 squared is 81, plus 18 times negative 9, can't quite remember, but that's okay. 18 times negative 9 plus 162. And I think if you work this all out, this ends up being the square root of 81. And the square root of 81, of course, equals 9. So the minimum is at negative 9, 9. Now we want to try and determine, is this an absolute minimum or just a relative one? And what we have to do is we have to go back to the original. The original is the square root of x squared plus 18x. This is going to be a minimum, an absolute minimum, and everything else is going to be above it because this is in the shape of a parabola. So it's going to be an absolute minimum to answer the question. And the final example dealing with the first derivative test. This is called the first derivative test that helps us to determine is it increasing or decreasing, or where is it increasing or decreasing, and as a result we should be able to tell is that a minimum or a maximum. Okay, number 7, we have g of t equals t cubed over 3 minus 13 halves t squared plus 36t, and we are told specifically 0 is less than or equal to t, which is less than infinity. In other words, t can only be 0 or positive. T can't be negative. Okay, we need to find the function's extreme values and tell which ones are absolute, which ones are relative. Okay, first thing we have to do in order to find extremes are to find the derivative. G prime of t equals, okay, the derivative of that will be t squared minus derivative of this will be 13t. Derivative of 36t is 36. And so now what I need to do, since I know that the extremes occur where the derivative equals 0, because of the slope has to be 0, notice how everything is connected. Then all I have to do is say 0 equals t squared minus 13t plus 36. Let's see, I believe this factors to a t minus 4, t minus 9, which equals 0. So I can set t minus 4 equal to 0 and t minus 9 equal to 0. Or in other words, t equals 9 or t equals 4. So now that tells me something occurs. Not a very good line at all there. That's okay. I know something occurs at 4 and something occurs at 9. So now I am going to have 3 test values. I'm going to choose 0 here, I'm going to choose 5 here, and 10 here. Those are just some values. If you really wanted to, you could plug in 4.26351 if you wanted to. I don't know why you'd want to do it. Realize we have to deal with e's here. Okay, so now I'm going to plug in, you plug these values into f prime to determine if it's increasing or decreasing. So f prime of 0, no, it's not f prime. Better be talking about g prime. G prime of 0 would be 0 minus 0 plus 36, or 36. So that means it's positive, which means it's increasing. If I plug in 5, G prime of 5 equals 5 squared is 25, 13 minus 5 is 65, plus 36, which equals negative 4, or it's negative, which means it is decreasing. And then here at 10, G prime of 10 equals 100 minus 130 plus 36, which equals a positive 6, or this will be positive, which means this is increasing. So we get, it's going to be increasing here, all of a sudden it starts decreasing again, and it continues to decrease until it starts increasing right there again. Now realize this graph doesn't have to look terribly important, but we have something that occurs here, something that occurs here. A maximum occurs here, a minimum occurs here. And so what we need to do is we need to find those particular values. So if I plug in g of 4 to find out what the y value is, g of 4, now this time we have to plug it back into the original. So g of 4 would be what? 64 thirds minus 104 plus 144, which ends up equaling 184 thirds, doing the arithmetic. And so we know we have a point for 184 thirds. Well, and we know that's a maximum. We just don't know if that's the absolute maximum or a relative. We'll deal with that in just a second. Then we have a minimum at g of 9, or at 9. So a minimum is going to be at 9 something, and to find that something, we're just going to plug in 9 everywhere. So that becomes, when it's all said and done, that ends up equaling 81 halves. And it's just plugging in 9 into g, not into g prime. And so we get 9 81 halves. Once again, we'll determine if this is relative or absolute. And then, and understand, we have t cubed. And if you think about the way t cubes look like, they look like this. So our gut instinct would be, well, they have to be relative. There's no absolute. But there's a slight problem here in that we don't start until x equals 0, or t equals 0. So we may actually have a point way down here, or we might have a point, well, we may have a point here, or the point may be here. But the point, what we need to do here is we need to check the endpoint. The endpoint occurs at 0. So now we have to figure out what is g of 0, because we know we have something at 0 something. Well, g of 0 would equal 0. So we have something that occurs at 0, 0. So now we have to look at these and put it into a little bit better of a graph. For 184 thirds, that's right here. So this is at 4. No, this is at 184 thirds, sorry. Here we have at 9, it's 81 halves, is where this occurs. And at 0, this is occurring 0. So now so we know that 0 would be a minimum, just by thinking it through like this. But now we have to determine which ones are relative, which ones are maximum. Well, what's the absolute lowest point that there is? There's this one right here. So this is an absolute minimum. Where's the absolute highest? Nowhere. I mean, the highest, it's going to go on forever and ever in this direction. So we know that this for 184 thirds would be a relative maximum. And then finally, this is a minimum, but it's not the absolute minimum because we have a minimum smaller down here. So this would be a relative minimum here. And so to answer this question, we have a relative maximum occurring at 4 184 thirds, a relative minimum at 9 81 halves, and an absolute minimum at the endpoint 0, 0. The big thing about question number 7, make sure that you test any endpoint. An endpoint will be either a minimum or a maximum. It may be a relative minimum, or it may be an absolute minimum, or maximum as well. But that's why you have to do some thinking on what does this graph look like.